So the equilibrium constant is how we can quantify these concentrations. Looking at our generic alphabet equation here, this is known as the law of mass action, and I think that's the only time we're going to say the law of mass action. This is how we write the expression for an equilibrium constant. The equilibrium constant is equal to the concentrations of the products over the reactants, and these concentrations are raised to a power that corresponds to the coefficient in the balanced chemical equation. And this is what we learned we could do for elementary steps for rate laws. Only elementary steps. We wish we could do it for everything, but we can't. But in equilibrium and the equilibrium constant, we do get to do that. I used to have a hard time remembering which was on top and which was on the bottom. We use delta a lot, the change in. Delta is always final minus initial. So this guy is final divided by initial, if that helps. So these are molar concentrations, and this is just a note. You see this K and that K and how they're not exactly the same. So that's the abbreviation for Kelvin, and this is the equilibrium constant.
I don't like that.
I know.
I can't write in italics.
That's okay. There's really not going to be a situation where that needs to be specified in your handwriting. It's mostly contextual. But like on an exam, bless you. And definitely in the slides, we're going to follow this pattern, just so you know, because what usually happens is if it's a constant, if it's a unit, if it's a unit abbreviation, it's going to be not italicized. Anything that's standing in for a number is like a variable, is going to be italicized. Because, we used up all the letters, so big K, little k, italicized K. Happens with the M's too. Okay. What's the correct expression for the equilibrium constant for this reaction? D. So the product is C, so that goes on top, and there's 3 of them, so it's C cubed, divided by A squared times B. Okay? Here's an actual chemical equation. The equilibrium constant is going to be equal to the concentration of NO2 to the 4th power times the concentration of oxygen to the 1st power. We don't write the 1. Divided by the N2O5 concentration squared. So the coefficients become the exponents. It's really important to see how this works, because when you see it, it's easy, which is actually how most of chemistry is, except for quantum mechanics. Once you see how it works and it makes sense to you, then it's really easy to understand and remember and all of those good things. The problem is it's sometimes quite a struggle to get to that point. This is something that we can all get to right now. It's a pattern. Okay, express the equilibrium constant for the combustion propane as shown by this balanced chemical equation. So the equilibrium constant is equal to the concentrations of the products. So we're going to have CO2 to the 3rd power because of that coefficient, and H2O to the 4th power. Ooh, that's kind of a sketchy 4. Divided by the reactants, C3, H8, that has an unwritten 1 as its coefficient. It has an unwritten 1 as its exponent. O2 to the 5th power. questions? So when K is big, much larger than 1, and that's not like 10 being much larger than 1. That's something like 1.9 times 10 to the 19th. That's much larger than 1, right? Some of these equilibrium constants are huge. I mean, they're just really, really big. What that tells us is that the concentration of products must be large and the concentrations of reactants must be small in order for K to be a big number. Does that make sense? So a large equilibrium constant tells us the equilibrium lies far to the right. A small k, much less than 1, as an example, 4.1 times 10 to the negative 31, right? Super, super small. Well, that means that the reaction concentrations are big and the product concentration is small. So small equilibrium constant favors the reactants. With an equilibrium constant this small, if you were studying this reaction, it would probably be hard to even detect the no that's in there. There's going to be some, but it might be so small that you can't detect it with whatever method. And so it looks like the reaction didn't happen at all. But it does a little tiny bit. So the equilibrium constant, again, doesn't tell us anything about how fast the reaction gets to equilibrium. It only tells us about what the equilibrium is. If you want to know how fast, you have to go back to chapter 15 and find the rate constant. So this is a summary. If K is approximately equal to 1, then neither direction is favored, and it's going to go roughly halfway. And so this is numbers like 10. It's going to be kind of balanced. Here's another slide that has colors. And it really should have some difference in shapes because on your black and white slides, they all look the same.
They really do. Huh?
Yeah. So I am circling the red ones. So you can circle the red ones on your page so that when you come back and look at this later, it will make some sense. 3 identical pictures and they picked this one. Why is that? Okay, this is representing A forming B, and A are the red ones and B are the black ones. And this is at 3 different temperatures, temperature 1, 2, and 3. At which temperature is the equilibrium constant the largest? Well, what does a large equilibrium constant mean? More products. And what's the product in this? It's B, the black one, right? So which of these has more black ones relative to red ones? C. That make sense? Yes.
For clarification, you circled the red one?
Yes.
Okay.
That's okay. And that's another example of why this shouldn't even be on a color slide, because there are people that have a hard time telling the difference between the red and the green. The red and the black. Then there's people who just don't know the names of their colors. 4 of my 5 sons are somewhat colorblind. So, yeah, we've had some interesting arguments about what color things are. So, the equilibrium constant, how is it changing? Well, it does change with temperature, like rate constants change with temperature. Any questions? So here we're told, for again this simple equilibrium, that the constant is 10. And initially, the reactant is 1.1 molar and there's no product. So at equilibrium, which of these statements is true? Well, let's just think about this. An equilibrium constant of 10, that's relatively close to 1, right? So we're not going to have extreme numbers. But is that bigger or smaller than 1? It's bigger, right? And that means we expect products, right? So then when we compare these first two, here we have mostly reactant and little product. And down here we have a little reactant and mostly product. So which is the answer? B. C is wrong because it's not going to be equal. Any questions? Do you remember Hess's law from Chem 1A? Does anybody remember hearing about Hess's law?
I remember
Yeah.
Mr. Hess.
Okay. When we did Hess's law, we were looking at the energy change for a reaction, delta H. And we learned that if you had a reaction that could occur in steps, the change in energy for the overall reaction was equal to the sum of the steps. And so in one icky part of lecture, we took these equations and we're rearranging them and doing stuff to them and adding them up and doing things like that. We're going to do a little bit of that again. If you reverse the reaction, then delta H would change sign because it was going backwards, right? And so if heat came out forwards, then it went in backwards, right? If you doubled all of the coefficients, you've got twice as much stuff reacting, the energy change is going to be twice as big, right? So we learned that. This is similar, but it's like escalated, right? So if you think of adding and subtracting as a lower level and multiplying and dividing is higher, right? So here we're not adding and subtracting, we're multiplying and raising to exponents. Okay, so I am not going to require you to show me these sort of derivations. I'm only showing them to you so that you believe me that the rules work. So a lot of times it's like, I understood it when she was talking about it, I can't remember it now. But it made sense then, so we'll just go with it, right? So the equilibrium constant for this guy. This is the inverse of that. Everybody see that? If you upside down it, if you invert it, make the numerator the denominator, they're the same. So writing the equation in the opposite direction, it would be the equilibrium constant to -1, or 1 over the equilibrium constant. So K reverse is equal to K forward to the -1, which is the same as 1 over K forward. So that's rule number 1. What if we multiply the coefficients? We're going to raise the equilibrium constant to the same power. So before, when we doubled this, we multiplied. Now if we double it, we're going to square. So let's see how this works. So it's the same equation. Over here, it's a little bit different. These have been multiplied by a factor n. So we've got C, and the coefficient is 3 times n, and n is just going to be some integer. Down here we have A to the n, A, and B to the 2n. This is equal to So K prime is equal to K raised to the n power. Any questions? If you add two equations, instead of adding delta H's, you multiply the equilibrium constants. So here A going to 2B going to 3C. If we add these equations together, we see that the two B's get canceled out, because that's like an intermediate. It was formed and then it disappeared again. And so the overall reaction is A is in equilibrium with 3C. So if we have the equilibrium constant for the first one times the equilibrium constant for the second one. So this guy times that guy. Well, the B squareds cancel out. And this is equal to C cubed over A. So they were calling these K1, K2, and K3. So if we look at the equation for K3, it would be C cubed over A. Cool. I like math, and math is even more fun when you find a practical application for it.
It's better.
Any questions? Okay, we got A going to 2B. We're told the equilibrium constant is 0.01. And we're asked, what is the equilibrium constant for B in equilibrium with 1/2 of A? We need to compare these two chemical equations and identify how they are different. What's one difference? The coefficients, right? So this was a coefficient of 2, and now it's 1. This was 1, and now it's 1/2. So the coefficients were divided by 2 or multiplied by 1/2. So then we're going to take that equilibrium constant. Oh, come on. Oh. They let me out of the house this morning. I don't know why. There's the equilibrium constant. So if it's multiplied by 1/2, we raise the coefficient, the constant to 1/2. What else is different between these two? Here, A is a reactant, and here, A is a product. It's written backwards. What do we do when we write it backwards? Upside down it, 1 over. So you can do that just by making the exponent negative, or you can write 1 over 0.010 to the 1/2 power. So, what would be the value of either of these? They're just the same. 10.
10.
Mm-hmm. Yeah. Any questions? You can do it on your calculator if you don't believe me. Yes?
More complicated questions like this,
Mhm.
and we use similar approach, we got through.
Well, those are the only 3 rules.
Okay.
And how it will get complicated is that you might have like 2 reactants that are nitrogens and oxygens in weird combinations, and 2 products that are nitrogens and oxygens with different numbers. And then it's challenging to make sure that you're copying them down correctly, right? And could give you 3 equations that you have to add together to get the final one, or say, here's the final equation, and what's the missing one in the middle? Things like that. But reverse it, invert K. Multiply coefficients raise k to a power. Add equations, multiply k. 3 rules. Any other questions? So this one's a little more complicated. So here's our chemical equation, and here's the equilibrium constant, 2.2 times 10 to the 6th, at 25 degrees. Again, like with the rate constant, they're often going to give you a temperature or say at the same temperature, and that's just, covering the bases. Because if you change the temperature, the equilibrium constant changes. And so they're just being specific, as scientists should be, that it's at the same temperature. We're asked to calculate the equilibrium constant for this reaction. And so we're going to look at this one, and we're going to look at that one, and see that they're similar yet different. So how are they different? Yeah, this one's been multiplied by 2 compared to that one. And the other thing is it's been reversed. So I'm going to do the reverse first. So just reversing it, we've got CO2 plus CF4 in equilibrium with 2 COF2. K equals 2.2 times 10 to the 6th before we reversed it. Now what needs to happen? This was the original. We need 1 over that. Actually, let's keep the number out of there for right now. And say K becomes 1 over K. Okay? And then we're going to multiply all the coefficients by 2. And what do we do here? We square it. We don't multiply it by 2. We raise it to the power of 2. Raising to a power is, in my mind at least, a higher math operation than multiplying. Multiplying is a higher math operation than adding. So what we're looking for is 1 over 2.2 times 10 to the 6th, the quantity squared. We can't just mess with the exponent on the scientific notation here. We're actually going to have to do math. And if you're not using the EE button on your calculator, you need to start doing that right away. It's painful to watch. So I'm going to do 1 divided by 2.2 EE6. I don't need any parentheses. I'm going to press equals, and then I'm going to press the x squared button. And so I've got...
If I want to use parentheses.
It won't kill you if you want to use parentheses. But what happens is if people are dividing by 2 numbers, they'll put parentheses around them and think they're okay to multiply. But that only works, oh, that's right, that doesn't work. That only works if you've got it around the quantity.
Oh,
Yeah.
makes sense.
Yeah, so these are some things where you might have the math written out right, and then you punch it in your calculator wrong. So watch out for that. Any questions? Okay, this one's a harder one. Predict the equilibrium constant for the first reaction, given the constants for the second and third reactions. So what we need to do is find out, well, how can we combine these 2 equations to get that one? And, You know, even if you don't have any dyslexia or spatial issues or anything, these start to swim together. So what I'm going to do is I'm going to use colored highlights, which hopefully nobody's colorblind and dyslexic, because that's going to be rough. I'm sorry. I can only do so much. I'm going to make water blue. You could like do a dashed line under it. You could circle something else, etc. And here's H2O, and that's going to be blue. I'm going to make, so I highlighted everything and then accidentally paused the video, and we're back. So this is the guy we're trying to make. And you can approach this in many different ways. I found a more organized approach. I'm going to look at the first one. The first reactant in the equation I'm trying to make. CO2 is a reactant with a coefficient of 1. So I'm going to look in these equations and find CO2. Well, it's a product here. So I'm going to take this equation and write it backwards so that the product becomes a reactant. And I'm going to leave off all those state symbols because they're all just gas. So let's call this K prime. There's too many numbers on this page already. So it was this second equation. We reversed the equation, so what do we do to K2? Invert it. Yeah, 1 over K2. So that's going to be 1 over 1.0 times 10 to the 5. Okay? We're going to mess with the equation. We're going to correspondingly mess with the equilibrium constant and move on. So next up is 3 hydrogens. We already have 1 hydrogen here, so we need 2 more. The third one has 2 more. Yeah, it's like, wait a minute. No. So this one has 1. If we put this guy in there with H2 as a reactant, these will add together and give us the 3 that we need. Maybe so. We'll find out, won't we? It's helpful to copy the right equation. Carbon monoxide's red. H2 is yellow. Methanol is green. What did we do to that equation? Did we change it? No, we just copied it, right? So the K for this one, maybe we could call it K double prime, is just equal to K3. We don't need to change it at all. Okay? Any questions? We've used both of the equations. If everything works out okay, we should be done. Because in these problems, they're going to give you only the equations you need. You're going to need to use all the equations. So that can be helpful to know. If you're doing this in real life, you're looking through the CRC with all these possible equations and trying to put together, and there's just so many options, it's really tough. But mostly people already did that for us already. So we're going to add these two together, and as Brandon predicted, the the carbon monoxides are gonna cancel out. So we get CO2 plus 3H2 in equilibrium with CH3OH plus H2. Oh. I meant to say it that way. I swear I hit the yellow. Okay, then, when we add them, this is now K1 that we were looking for, right? This is, we're gonna multiply these two equilibrium constants. K prime times K double prime. So K prime is 1 over 1 times 10 to the 5th, and double prime was 1.4 times 10 to the 7th. Practice using your EE button. 1.4 EE7 divided by 1 EE5. Any questions? That's section 4. Yeah. It turned out rather pretty, didn't it? I put the graph paper in the background here so I can write straight. And it also helps me keep things the right size. Because what I love about this program is I can zoom in the bottom. But then you sometimes lose context for how big your things are, right? And so I've got the squares to remind me, this is about how tall the letter should be.